Let's begin the session, friends. And to start with, yesterday we discussed about Hadoop architecture, Hadoop components, right? And as part of the architecture or as part of the components, we discussed about HDFS. And for HDFS, the primary features that we need to talk about is the partitioning feature and replication feature, right? So when we talk about components, Hadoop has three major components. HDFS, this is the file system, and this solves the storage challenge for big data. Then we have MapReduce, which is basically the computing framework, which solves the processing problem of big data. Then we have Jan. Jan is the cluster manager, which is enhanced version of the services in Hadoop 2.x version. Now, when we talk about HDFS, the storage component, we need to look at its capabilities with respect to partitioning and replication. This allows Hadoop to handle large or big size data. And when we talk about partitioning, what is the default partitioning size? Very good. So partitioning is done based on standard fixed size splits of data. And this split is called as block. And the standard or fixed size is 128 MB as the most practiced.
Hey, kai ko nahi aa raha thi?
Who's that?
तुम्हारा काय है? मेरे को नहीं आ रहा. Accept नहीं किए.
Yeah, I put everyone on mute. I think this is the only way I can control the background noises. If you want to ask anything, just raise your arm, raise your hand so that I give you the unmute option. Right. So we're talking about partitioning, and the default block size is 128, and the least or the minimum block size that we can go to is 64 MB. And any block size which is multiples of 64 can be used. Next, with respect to the replication, that is making the copies of these blocks so that we do not lose the data, right, is done again using a standard procedure. And this replication by default makes 3 copies, right? Replication factor is 3 default. We can alter these these values with respect to the block size or with respect to the replication. We can give that setting. We'll learn where to give those settings, what files we have to edit when we do the hands-on, when we do try to install them. All right, so this is about the components. Next, when we talk about the architecture of Hadoop, always remember the distributed frameworks will come with master-slave architecture, where one of the component in that particular clustered environment will act like a master. The remaining components in that network will follow the instructions which this master is giving us. Right? So that's master-slave architecture. Now, this master-slave architecture and the components are basically supported by the Java services which run in the backdrop. Right? Background Java processes. And we call them as daemons. And in Hadoop, we have 5 daemons. And these daemons are name node, data nodes, resource manager, node manager, and a secondary name node. Right? These are the 5 services which run in the backdrop. And whenever we talk about HDFS, remember, HDFS is the storage component, and here we have name node, and always you will have one name node, and this is the master. Then we will have data nodes. Data nodes will have multiple data nodes, right? And there will be maybe n number of data nodes that you will have, and these are the slave components, right? And then we will have secondary name node, which acts like a backup of your metadata of name node. So these are the 3 components which support HDFS, and we'll focus on these things. After we understand these services, we look into the resource manager and node manager, which also alternatively are called as job tracker and task tracker, or I should rather say they used to be called as job tracker and task tracker. The latest versions, we call them as resource manager and node manager. This is the architecture, basically, how Hadoop has actually started. Now, the master is the single point of contact, and the clients would interact with the master. Right? That's your name node. And name node takes the request that is coming from the client, splits that request into tasks, and assign the tasks to data nodes, slave nodes. Right? For now, we are only talking about storage requirement. So if I have a 2 terabyte file, which I need to copy, name node, using its metadata information about all the data nodes, will identify which data node can take the block, the data. And data node will give instruction to that particular data node and asks it to copy that content. So data node will access the file and copies the block. Right? This way. So this data node is getting again another instruction. This data node is also getting another instruction. So these are going to, right, get the blocks. This is how name node controls the entire operation in the Hadoop architecture or Hadoop environment. Okay, I see a lot of people are joining at their leisure. Okay, it's 8:44 now, and I still see people joining in. Right? Please join by time. I for every time, every session, I give 5 minutes grace period. Right? We start only after 5 minutes. So make sure you join on time, guys. Next, we are talking about the name node. Abhishek, did I talk anything about Apache Pig? Did I tell that we're starting today? We have to cover theory. We have to start working with the services. It's pending. It will cover Apache Pig. Concentrate on what we are discussing now. Why you want to learn Pig? I wantedly did not answer that question. We have time. Let's finish this first. Yeah. So name node, guys. Focus here, please, everyone. So we're talking about the first service in Hadoop. Right? 5 services are there. Remember, we are talking about the most important service, which is name node service. And this is I should say, the single machine or single service which manages the entire cluster, right? So very, very, very important service. And what does it do? Yesterday we discussed, remember, it is only doing namespace operations. Your manager is going to manage the team. And without manager, there's no progress, right? The entire team becomes chaotic. So it becomes very, very, very important node. Remember that. Most important machine in HDFS. And what does it have? It has metadata. It does not have client data. It will have metadata, data about data, right? Now those metadata files in HDFS, in name node, 2 files are there. And those files are called as FS image, and another file is called as edit logs. Right? What are these files? What does these contain? We'll discuss that. Let us first try and finish this. So name node, important machine. It contains only metadata. It does not contain the actual data of the client. It does the operations which basically help us to manage the cluster. Internally, using this metadata, it can map the blocks to a file. It also tries to map the information of replicated blocks, everything about blocks basically, and of course nodes. Which block is stored in which node, right? And which blocks, which set of blocks would give us the file. So all that information can be mapped using the metadata files. Then we also have discussed about balancer, right? It will try to balance the load on the data nodes. Now it would also manage the replication factor. Replication factor means, replication means copies. Replication factor means at any given instance, given second, given moment, you need to have the fixed, prefixed or set replications in your entire Hadoop cluster. That means if you say replication factor is equals to 3, which is default, then at any given instance, you need to have 3 copies of every block, right? So if I have multiple nodes, make sure the block is copied in 3 different servers. Let's say here, here, and here. When I say at any given instance, what if this instance goes down? At any given instance, there should be 3 blocks. 3 replicas. That fault tolerance is managed by name node. So it identifies that the node is failed and it will create replication immediately. Right? 3 copies should be there, not just 2. Remember that. So let us see how it works, right? Replication factor, will detail that. But before that, let's try and understand what does data nodes have. So name node only metadata and controls the operations. And the slave nodes, these are your slave nodes. You will have multiple nodes also. These nodes actually do the read-write operations. These nodes are responsible for dealing with the client data. Right? These are responsible. Right, Vijay, I'll give you an update today. I promise. I'll let you know. Right. So original client data is getting managed. It does the read-write operations. That means storing the data into the blocks. Into the storage. Right. This way, you can see these are the files. Now this file input.txt is actually having 2 blocks. The blocks are 1 and 2. Block 1, block 2. So this is the metadata which name node consists of. right? Now it also has additional metadata, it's not given here, which would also talk about which node contains these blocks. So node 1 has 1 and 2 files. Node 2 has block 2. Node 3 has block 1. Right? So it will basically have the information like this. So that's your metadata. Okay. So this is how your data gets loaded into your data nodes. It's nothing but storage. That's it. Now, the data nodes also have additional tasks that they do. The task is about informing the name node, the manager, the master, about their functionality, their, I should say, availability. So in a team, if you have a manager, though manager is monitoring the team, it is expected by the team members to give update to the manager voluntarily. You go and give update, right? That is the expected behavior. You report to manager. So same way, data nodes also have to report to name node. Now here that reporting is done using a concept called as heartbeat. What is this heartbeat? Heartbeat is nothing but an empty signal, empty message, a data transfer, right? An empty packet is transmitted from data node to name node at every 3 seconds. Default. This basically informs name node that these data nodes are up and running. It's just like our heartbeat is, right? We have our heartbeat, right? So this heartbeat basically tells us we are alive. Same way, this heartbeat signal that we are talking about, which is an empty message or empty signal, will inform name node that these data nodes are up and running, alive. And additionally, every 10th heartbeat, that is 30 seconds, block reports are sent. Block reports means how many blocks are filled in, how many blocks can be filled, right? That storage information is shared in that message. 10th heartbeat would not be empty. It would contain block reports. This basically allows name node to record how much data can be stored in each of the data nodes when a new requirement is coming in. Right? This information will give name node an idea on which data node can be used. Right? And name node has an additional duty for data nodes. Data nodes are responsible for informing name node that they're alive and all that. And name node is the manager, right? So it basically maintains the replication of the data. So it replicates data node blocks if the data node fails. This is how name node maintains replication factor at any given instance. Now, what is this heartbeat? What exactly is replication factor and all that? Let's try and understand that. What happens basically here? This is an image. Assume we have name node. This is your master, right? This master will have metadata, and it also has rack awareness. Metadata and the combination basically will tell us what nodes we are using, and in each of the node, what blocks are stored. Right? This is the information. So we have rack. In rack 1, we have data node 2, data node 3, let's say data node n also, or data node 5 also is there, assume. Then we have rack 5 where data node 3 is there, rack 9, data node 8 is there, so on and so forth, example, assume. Now, each data node that you see here is responsible to share heartbeat signal to name node. At every 3 seconds interval, automatically there an empty message goes to name node, and this empty message, when received by name node, will understand that data node is up and running. Now this data node 3 did not send a heartbeat. It might be crashed out, so it did not send heartbeat to name node, right? So when your name node does not receive this heartbeat signal, it will understand that the node is down. There's a missing replica. A node is missing, right? This node did not respond. So immediately the metadata will tell us that node 3, which contains A and C blocks, are not accessible. So we will have missing replicas, right? So using this metadata and rack awareness script, name node will instruct node 1, which also has the same blocks, to copy those blocks to node 8. Why node 8? Maybe there is node 5. Let's say there is node 5 here. Why node 8 and why not node 5? Anyone? Yeah. Anyone? Why not node 5? Why node 8? Very good. It took so much time to answer. Node 5 here is in the same rack. Remember the copying yesterday? We discussed about how does the data get copied into the your nodes, right? We already have node 1, node 2 in the same rack. So at least one copy should be there in a node which is in another rack. So I cannot take node 5 because it is in the same rack, right? Node 3 is in another rack if you observe, but this is done. So immediately node 1 gets the instruction to make a copy of those blocks in another rack, rack 9, node 8. This is how replication is handled if or in case a data node is failed. Right? So this is how the basic functionality is there in your Hadoop. Missing heartbeats signify the lost nodes. If your name node does not receive heartbeat signal, that means data node is died. Data node is not available. Name node consults metadata, finds what is the data which is getting affected because of this node down. Then we use rack awareness script and identifies what would be the other node that I can use to make the replication. A name node gives the instruction to this data node to copy those blocks into a new node. Is this flow clear? Very simple, straightforward flow. Is it clear? Wonderful. Okay. What happens if node 3 is after doing some work missing? After doing some work, I didn't understand. We are not talking about work, Anita. We are only talking about storage now. Right? So the current scenario is these blocks are copied into these 3 nodes. Storage is already there. The blocks are already copied. In midway, this data node failed. In such cases, your name node kicks in and makes sure that the replication is maintained. Got it? Yeah. that information is not available anymore. So why is it crashed? That's something that we need to understand, right? It is completely unavailable. So your admin would come into the picture. He would make sure that the files, the node is basically refreshed and then attached to the name node. Yeah. Muthu, you also? Did you understand? Muthu Krishnan. Yeah. So once it is down means that information is flushed out. It becomes fresh. Right. So this is about data node. Then we have something called as safe mode. Right. We'll also see what does that safe mode means. Okay. So we will be one more replica made, sir, in case of crash, total 3, right? Rajni, I didn't understand again. See, at any given instance, we are saying there should be 3 copies. Initially, it was 3 copies. 1, 2, 3 initially. But because of some reason, this node got crashed. So immediately, name node would make sure that replication is maintained here. So this becomes 3rd copy. But at any given point of time, 3 should be there. Yeah. All right. Next, let's talk about something called as a safe mode. Now, how many of you have seen this message when you are starting to access your Windows system? Booting time, it says Windows entered safe mode. Generally, you will see that black color screen, right? Windows is booting in safe mode. Do you want to start it normally? At least few people might have seen that, assume. Yeah. Especially if you are using a desktop, for sure you would have seen that. Whenever there is, sudden shutdown, exactly. If there is a abrupt shutdown, then it's not a graceful shutdown. Then a lot of information is not clearly written. Right? So what happens is the system goes into something called as safe mode. Now I'll talk about it in Hadoop case. Now what happens is in Hadoop, everything is managed by name node, right? Your name node maintains the entire flow of your cluster, right? Now, what happens in name node or what happens in cluster is that when there is a task, when you want to store the data or when you are doing some kind of a task, name node will assign the task to data nodes, right? And this information is updated generally in the metadata. Yeah. Now let's say you're starting your server. Safe mode occurs when you just started your server, right? So let's say you're starting your service, Hadoop services. After, let's say, some kind of an issue or something happened and you're shut down your services and you're starting your service. Now, what happens is when the service is started initially for a few minutes, your name node puts the entire cluster in a safe mode. This safe mode basically means read-only mode. Why? Why it has to do this? What is happening here is name node is first recording the instructions in edit logs. Your metadata, right? It records the instructions which it is giving to the data nodes. in edit logs first. These edit logs are also known as write ahead logs. Val. So first name node would write the logs and then pass that information to the data nodes. So before the transaction is happening, the record is getting updated in the logs. Okay, the task is getting updated in the logs. Remember this. Now let's say you shut down the services and you restarted the services. At the start of the service, name node is referring to the metadata, and it is trying to compare the status of all these data nodes for consistency. It has to start the services, means everything should be consistent, right? So it verifies for that consistency by looking into the current status of each data node and maps that information with metadata it has. So every update will actually, any transaction that you're doing in data node, any task that you're doing, will actually be assigned with a unique ID, and that change gets recorded here, and there will be a unique ID for the status. Right? Each status change, each transaction that you're doing will assign a unique ID. It would be like a counter, 1, 2, 3, 4, so on and so forth. So when it is verifying these changes, it will see whether the current condition in edit logs and data nodes conditions are same or not. If they are same, only then you say it is consistent. If it is consistent, then you are going to allow any kind of transactions on your Hadoop cluster. But if there is inconsistency, that is when the challenge comes. Your metadata says something, your name node is being given some information, but your data node is doing something. It's like your manager has status that 80% of the project is completed, but when you actually look at the task that is being done by the peer team member, it is only 30% done, or 40% done, or even 70% done. That mismatch cannot be managed by, that should not be there with the manager, right? There should be no mismatch. So that is what we are trying to capture, or Hadoop is trying to capture that mismatch when initially the services are started. And in that few minutes or few seconds sometimes, when name node verifies the status of data nodes, right, it will keep the entire cluster in read-only mode. That is called as safe mode. This is also clear, everyone? Safe mode. Wonderful. Very good. All right. Now, what is FS image? Edit logs, we just understood that is write ahead logs. So these logs will be constantly be updated, right? These are dynamic. As and how any change is happening in that entire cluster, edit logs will get updated. Now, what is FS image? FS image basically means file system image. Now, this file system image is like a snapshot, or you can say it's an image of the current condition of your system. And this is static. What does that static condition means is when you are shutting down your services, let's say Hadoop services are getting shut down. So at that stage, the final consistent status of all the nodes is recorded as FS image, right? Consistent status of all the nodes, data nodes, is recorded in FS image. It's like you're taking a snap. picture of your current situation, right? That's your FS image static file, and it happens only when your services are shutting down. Now, when the services are up and running, FS image does not get edited. It is a static file. Remember, you will not touch it. Only the edit logs keep getting updated, right? So any transaction, first it is recorded in edit logs, then the transaction gets executed. Okay, so that's the flow. Now, in let's say in any service, not just Hadoop, any service that we talk about, do you keep shutting it down every now and then? We're talking about an organization services. For example, Facebook or Yahoo or Google, you take these services. Do you regularly keep shutting it down? Never. Never you shut down, right? Zero downtime is what we need. Now, if you're saying zero downtime, that means your service will never get shut down. So in such cases, your static file, which is FS image, will remain same. It will not get updated. FS image is created when you have shut down your services last, whatever the last time you have shut down the services. By updating all these current status to FS image, you will update it, right? This is your file. Now, in 5 years or 10 years, you are not shutting down the service. So what happens? This file becomes very, very old, historic, and your edit log files will become such a big file that you cannot manage it. Because it is not getting flushed and updated into FS image, right? So edit logs keeps updating. It's getting updated. So it becomes a file which is too big to handle. Very big, in fact, to handle. Right? Now, how do I overcome this problem? Because what if the service goes down? What if my service is, let's say I started the service, Hadoop service in, let's say 2010. Now in 2020, the service got crashed. So what happens? Your FS image is talking about right, very old status, 2010 status. And all these edit logs file, right, all the transaction details that edit logs is maintaining is crashed. It's gone. Because of this crash, edit log file is gone. So how do you basically come to know the status? Because when you restart your services, the data node's current situation should be mapped with FS image status, the IDs, right? Now, if that is not matching, then it will be in safe mode, data inconsistency. If you want to update your FS image file with edit logs, that file is lost already. So all the 10 years effort, 10-year transactional details are gone. Making sense? Completely gone. Now, to overcome this scenario, Hadoop introduced secondary name node. Secondary name node. It is also known as checkpoint node. Both are similar. Secondary name node and checkpoint nodes are both are similar. Now, what does secondary name node contain? As the name suggests, it looks like, or it gives an impression that it is the backup of name node. Exactly, like an assistant manager, exactly. But the concept is a little different here, okay? Your secondary name node is not a backup of name node, remember? It does not work like your name node. It doesn't work the same way. Okay. Secondary name node is only a storage device which maintains the metadata. Secondary name node only maintains metadata. Right? Now, there are two things that we need to look at. I mean, the services, the advantage of secondary name node architecture gives us two advantages. The work of secondary name node is just this. It does nothing except for one task. It copies to name node at every 60 minutes. That's the standard. Every 60 minutes, it connects to name node. Remember, in the metadata, in the name node, we have metadata, right? We bring that metadata to secondary name node. What does that metadata have? Two files, fs image and edit logs. We copy those metadata files to secondary name node every 60 minutes, right? And what is it doing? In the secondary name node, the fs image file gets updated with all the information that is there in the edit logs file. This happens at every 1 hour. And fs image will have timestamp as the name. It's just not fs image, but it has a big number. It includes some sequence number, and it also includes the status, which basically means timestamp. For example, at 8:30 p.m., we are recording the fs image, right? So here we will have fs image underscore 8:30, assume, right? 8:30 p.m. You can say 20:30. Now, after 1 hour, the edit logs, whatever the transactions that we are doing here, it's getting recorded in edit logs, right? That edit logs file will also get copied, right? And this information is getting updated into this old file. Now it is 21:30, right? 1 hour later, 21:30. This entire process happens. And once this file is getting updated, it becomes fs image underscore 21:30. Now this file is again put back into name node. So here the latest fs image that I'll have now is 21:30. Right? So your name node will constantly get your fs image updated. The static file that we have is getting up to date. Right? So if in case your node crashes down, the backup of that metadata is available in secondary name node. We are storing and update. We are basically updating the fs image, right? So this fs image is available in the secondary name node as a backup. So if name node crashes out, and when the admin is recovering that name node, we will be able to recover to the latest status using this current or latest fs image file. Right? Next, the another benefit by this process is we also have edit log files, which is dynamic file which constantly get updated. Any transaction that is happening first has to get recorded in the edit logs. So if you leave that edit logs as is, then that file becomes a very big file, isn't it? You'll not be able to manage such a big file. So we are controlling the growth of that edit log files as well. Right? So that is how we manage the metadata using secondary name node. The advantage is we'll always keep the static file, which is fs image, to the latest status. The second one is we control the edit log files growth. You can only have edit logs which can grow up till 1 hour time frame only. Right? In 1 hour, whatever the data that you can or transaction that you can perform, you are going to record that in the edit logs. So that's the max it can grow, because after 1 hour, anyways, this copying happen, right? Secondary name node contacts, takes the latest edit logs, takes the FS image. So as soon as this action is triggered, immediately the next edit logs, next transaction that we are talking about will be updated into a new edit log files. Right? Edit logs will immediately be created a new file, and this new edit log files will be updated now. So this way we are controlling the edit logs. Okay, from active to slave, I think there are a few questions. Let me take it. So we can say that it's like a switchover in database, not exactly like a switchover, but yes, very similar to that. Not from active to slave. That's not the concept here. We're talking about only files. Active and slave, you say that you're talking about service. That is Hadoop 2.x architecture. We're not dealing with services here. We are only talking about files. Files get copied. The work of name node continues. Right? That doesn't get hampered. It keeps doing whatever it is doing. Secondary name node in between copies these files and puts back the latest FS image into your name node. That's all it does, nothing else. Yeah, nothing stops, Mayur. Everything goes as is. Yeah. Right, so this is about your secondary name node transactions. It's not a hot standby. It backs up only the metadata. It connects to name node every 1 hour, copies the FS image and edit logs, and in secondary name node, the FS image is getting updated with the edit logs information, and then put that latest FS image file back to name node. So that is the transaction, or that is the task of secondary name node. Now there is one interesting thing that happens. We'll talk about that because that is a drawback. We need to talk about that as a drawback. We'll go there. Let me see another question. If I'm asking if name node fails, if name node fails, there are chances that secondary name node have 1 hour old info. That is the drawback, Mayur. We'll be talking about that. It's called a single point of failure. So that basically is data loss condition. Yeah, because of that condition only, we have Hadoop 2.x architecture also coming into the picture. We'll talk about those disadvantages. Yes, Ashna, you want to speak? Yeah, there you go.
Sir, sorry to interrupt. I cannot see the whole picture for this one because, for example, in the Hadoop, we have this active node, and then we have the slave or the secondary node, and then we have the data node, right? So where do we place the secondary name node? Is it like within the one server there are two nodes? I wasn't able to visualize that one.
You see this architecture, the screen?
Oh, okay. So we're still following this one.
Yes. This is just another system.
Okay.
It may be outside your network also.
Okay. It's now clear, sir. Thank you. I thought we jumped to another. It's now clear. Thank you.
No. You're still talking about Hadoop 1.x only. Right. All right. So these are a few of the things that we need to discuss. Of course, as I mentioned, there are drawbacks. We'll talk about the drawback also. What's the time? We'll have to start with MapReduce. So we'll take a small pause, and then we'll come back and discuss about MapReduce components, post which we'll talk about the single point of failures of your name node or Hadoop drawbacks. Right? So we'll come back. So we are basically trying to understand how these services run: name node, data node, and secondary name node. That is storage component. MapReduce is basically your processing component, right? So we'll have to start discussing this. It's 9:26 in IST PM basically. I should put that. So we'll connect at 9:32. 6 minutes. Yeah. 6 minutes break, guys. Yeah. All right. Everyone back, right? In name node, storage of edit logs will increase from time to time. How do we solve this? We'll have to purge this, Madhuri. That's what admins do. Big data Hadoop administrators, they actually need to remove the outdated blocks. And anyways, we'll write rules. Anything which is greater than 30 will automatically get purged. Got it, Madhuri? Yeah, sure. All right, so let's now look into the MapReduce component. So just to give you a picture, we'll talk about name node. Then we'll have data nodes. Let's say we will try to do this. So we will have name node, and these are the bunch of data nodes, right? So this is your master. And here, let's say we have slave. This is your slave nodes. Now these components are basically from your HDFS side. HDFS, right? So HDFS, master, slave, name node, data node. Now in the MapReduce, also we need to have, or we need to see, there is master node and slave node, because this is service different, right? You're basically doing processing. Here we are trying to solve the storage related challenges. Here we are trying to solve the processing related challenges. So this service is completely different, and here we will have something called as resource manager. Now this is the master, and that service can be run in any node. We generally take the master node only for running the resource manager services. So name node service, resource manager service can be in running in the same node, master node. And then we'll have node managers. So each slave node will have node manager. Just like how we have data node service individually working in each of the data node, same way we will have node manager running in each of these data nodes or slave nodes. This is the breakup, guys. This is how we basically have to see the 5 services, out of which 4 services are shown here. Secondary name node is basically a backup. Secondary name node is a backup of metadata. Right? So MapReduce was originally designed by Google. They modeled it, right? And that's how their big data is basically working. That's the logic that they use on their big data, Google's big data. Now, when we talk about MapReduce framework, the computation happens in two different functions. Map jobs or map function is a different task. Reduce function is a different task, right? And these tasks are getting executed on different nodes parallelly. Parallelization can be achieved, right? And to explain those services, to understand the flow, we have resource manager and node manager. Now, resource manager would take in the client's request. It's the manager, right? So it will get the request from the clients. And then that request is then subdivided into tasks. And those tasks are individually then assigned to different data nodes. Right? All these different data nodes will get that particular task. This is basically how the MapReduce transactions are conducted, basically are happening, right? Now, resource manager will assign the node task to the node manager. In the node manager, we will have node, in your data nodes, my bad. In the data nodes, slave nodes, we will have these node managers running in each of these individual systems, which is responsible to get the task executed. Resource manager is assigning the tasks to the slave nodes, in which you will have node managers which accept the tasks and get the task executed. Right? So that's basically the relation between resource manager and node manager. Previously, resource manager and node manager, they were called as job tracker and task tracker. Now your resource manager, which is the master, takes care of checking the machine failures, transaction failures, right, performance issues, and all those kind of transactional operational related challenges will be handled by your master, that is resource manager. Node failures, what happens if node is failed when a transaction is happening, right? Unless until all the transactions, sub transactions are completed, your main transaction is not declared as complete. So your resource manager keeps track of those transactions which are happening individually on different nodes, and then it keeps updating basically on the status of the transaction. So I was trying to give this breakup. We'll have a single resource manager, right? That is your master. For one master, you'll have one resource manager. And this is responsible for scheduling the jobs, right, on the slaves, right? And it also manages, or basically it monitors the node manager, that is nothing but your slave's progress, right? If any node fails, then resource manager will get an information about that failed node thanks to the heartbeat concept that we have understood. Same concept is applied here on data nodes and node managers and resource manager. Same heartbeat concept. So initially the heartbeat will have only the empty information, and at the 10th heartbeat it will also give us the status of the transaction task, and whatever the task it is happening, it gives us the status of that. Yeah, so that's basically how the resource manager is monitoring node manager transactions. Yeah, next. When we look into this, okay, let me talk about this. This is the flow. So when a client is making the request, it is directly going to the resource manager or your job tracker. And this resource manager, thanks to the metadata, it will understand which node is free. When I say free, from the transaction perspective, because edit logs will also have the information on the tasks, right? So it looks into that information and understands which transaction or which slave node is free to take a transaction. And those tasks or the assignment which is given by the client is broken down into subtasks, and those subtasks get assigned to slave nodes, and these slave nodes will have task tracker. We call it as node manager now. Node manager will be making sure that the required resources are obtained in this particular node, slave node, and the task is completed. In the interim, the information is shared to the resource manager about the status. Once it is completed successfully, that of course will also be informed to the your resource manager. And if by let's say any chance this node is gone, so the heartbeat information is not passed, so resource manager will know that one of the tasks which was assigned to this node is not complete. So if I have this task to be completed, these are subtasks. If this is not completed, rest all is completed, then still this will be under progress only, in progress status, unless until this task is complete, right? Subtask is completed. So here, because this node has failed, resource manager will know that, and it will try to restart that particular transaction on the same node. It generally tries to do that, right? If it fails, if the transaction fails because of some other issue, node is available, but maybe resources are not available or something on those lines, and the transaction is failed. So in such cases, it will look for alternative node on which the same transaction can be completed. So that automatic failover of the failed task is taken care by your resource manager, right? This is basically how your resource manager and node manager work. Right? So one resource manager per master, and you'll have only one master. And we will have one node manager per slave, but we'll have many slaves. Right? So that's the breakup. Now let us try and understand what does this actual map jobs and reduce jobs mean. This is the overall functionality, but what does MapReduce actually mean? MapReduce is a concept which was originally designed by Google using a low-level language. Right? You can use Java or C to write your MapReduce codes. Remember, MapReduce or Hadoop was developed in Java, right? Those days, Java was everything. So it was written in Java, which is basically called as low-level language. We can also use Python now. C++ is not there. C, Pascal can be used to write MapReduce codes. Now these MapReduce codes have to be developed in two parts: map and reduce. Map steps or map jobs and reduce jobs. If you remember the example that I have given for Google, let's say these are the servers. Let's say Amazon, okay? I want to purchase something in Amazon in 2021, January. So Amazon is maintaining its servers based on, let's say, year to year it changes the servers. Okay, this is 2010, 2011, 2012, 2013, so on and so forth. I have Amazon account way back in 2010 also. Okay, now we're talking about guys, right? One of the most popular e-commerce portal worldwide. So in Amazon, when we talk about this, we have different servers where Amazon is maintaining these servers for 1 year. So whenever there is some transactions happening, we record into the server, right? That's the basic understanding. You should probably be understanding this now by now, because we discussed one of these similar examples. Now, let's imagine you have an account, right? When I say account, you will have a unique ID, right? That's nothing but your email ID. And for that, let's say there is a unique number also given, 1, 2, 3, 4, 5. Assume unique ID. Now, if Amazon has to make some kind of personalizations to me, if I have to log in and purchase something, then Amazon is looking into my profile, right? Unless until Amazon will understand who I am. Somebody has switched on their cameras, please check. Yeah. So unless until Amazon will understand what I purchase, when I purchase, how I purchase, why I purchase, it cannot make recommendations, right? It cannot do personalization. Isn't it? So profile has to be created. But if you have to connect and create profile, we need to basically see what all things I purchased in the past also. Right? All these servers, we need to try and look into, so that we can map the details of this particular employee ID or email ID, or here it is customer ID. Right? Now, unless until this information is gathered, Amazon will not know what to recommend to me. Right? So how do we get that information? Because this information that we are talking about for this customer is stored in different nodes, distributed. Now, if you talk about Amazon data, it will have a lot of details, right? So from rows perspective, from the columns perspective, this is a huge amount of data. So what we do is we write a code, we call it as map task or mapper jobs. This map tasks will basically try to retrieve the information. These are only used for retrieval. So we will say, look into the transactions which 1, 2, 3, 4, 5 ID has performed in all the past servers. You look into all these records and see if that record belongs to the ID 1, 2, 3, 4, 5. Right? So maybe I have purchased something in 2011. So that information is extracted. So we get some information here from 2011. 2015. So 2012, 2013, I have not purchased anything at all. 2016, 2019, 2020. So this way, the required transactional details are captured. This is huge amount of data that we are talking about. From all that information, all that data, we are only looking into the transactions which 1, 2, 3, 4, 5 ID has performed. Now we are mapping to these different servers and trying to retrieve or map the ID to those transactions. Hence it's called as map tasks. And when we do the map tasks, it is, remember, a retrieval task predominantly. It will give us data, intermediate data, and this intermediate data will always be in key and value pair format. That means we are giving some structure. It gets some structure. Key and value pair. Right? Clear, guys? Making sense? This is your map job. Now, once you get this intermediate key value pair data, for example, this transactions, list of transactions, on this list of transactions, now I'll try to reduce this information to results. You perform whatever the aggregation steps you might want to do on the gathered data, and this gives us the results. Got it, everyone? Two fundamental parts, map step. Master node takes the large problem input and slices into sub-programs, subtasks. These tasks are assigned to individual nodes, data nodes. So master node is going to, resource manager is going to take the request, going to break it up and assign it, distribute it across to all the node managers, which are running on the slave nodes. Right? And these node managers are responsible to get the work done. So your data nodes will process that small task that has been assigned to that particular node and gives back the control to master once the transaction is completed, along with all the resources that we are gathering there. Then we have something called as a reduce step. Right? This reduce step is taking the information or data that is available here. Master node takes the answers to the sub-programs or sub-problems that we have at map step, and we combine all that answers into a specific format to get a final answer to the original problem. Right? That's basically how it is done. And this input data in this image, if you see, this input data is nothing but HDFS, which ultimately means disk of individual servers. So blocks physically are getting stored in different servers, right? So we are trying to retrieve that information from the map jobs. Right? Typically, it would be one map task for one task. Right? One map job is created for one task that needs to be addressed. That's not based on the nodes and all that, but typically we will see the number of or multiples of the number of data nodes, right, is what you are going to see for map jobs. Those many map jobs will be there. Now this map jobs will give us a intermediate data, hands back the control to master. So information is basically captured here. This is your key value pair, remember. And on this key value pair, we are going to further reduce it to get the result. That's it. So this is how your map and reduce jobs work. And when we talk about map and reduce tasks, input reader, this is the first task, which basically is splitting. So what is happening? Your task is getting split into smaller things, smaller sized functions. So divides input into appropriate size splits, which get assigned to a map function. Then map function is executed. This will map the files to smaller intermediate key and value pair results. Retrieval, basically. Then this is an optional field that we have, or optional step we have. compare function or shuffling function, sorting function, you might want to call that anything. Input for reduce is pulled from the map output, right? So once the data is available, you might want to do some kind of a sorting or pre-processing. That's your compare function. And after that is done, the data goes as an input to reduce function here. Now this reduce function is getting the final solution, right? And finally we have output writer. This is going to write the files onto the disk. I mean, it has to store the data back, right? So it writes the information back to the disk. So this is how we basically have our map and reduce jobs. Clear, everyone? Wonderful, yeah. Any questions, please post them. Now there is something called as input split. Do I have that? Okay, I don't have that. Okay. Now, if you observe here, what we are saying is we want to assign task to a slave node, right? Map task basically assigned to worker nodes, right? So let's take a small example here. Do I have? Yeah, I'll take this sheet, or let me write it here. Let's say I have a file. A very simple example. It's a very popular example. I have a file. This file is 400 MB and it has only 4 records or rows. Row 1, row 2, row 3, row 4. Okay. Each is 100 MB. Okay. Each row is 100 MB. Now, this is a single physical file. I want to store this into Hadoop. Store the file to Hadoop. What I do? If I have to do this, I need to look into the block. The block size is fixed 128 MB. Right? So what I do? I will create block 1. In the block 1, what would I have? I would have record 1, which is 100 MB. And then from record 2, I will have 28 MB. Right? Then I will take block 2. In block 2, I would have, how much data is left out, guys? 100 minus 28. How much data is left out here? Yeah. 100. Very good. So we have 72 MB, right? So I will take R2 again, and here I'll have only 72 MB. So remaining block, because I need to have 128 MB, right? So how much is the data which is left out? 56. Very good. So I need 56 MB. Now that 56 MB is coming from where? Next record. What is the next record? R3. So I'll take 56 MB. So if I take next block, what is the information left out? 100 MB minus 56, I will have 44 MB. This is R3, 44 MB data is getting stored. I'll put here. Let's assume we are putting it here. So how much is still left out? How much I need? Yeah, guys. Exactly. I need I have 128 MB, out of which I have 44 MB filled up. So remaining is 84 MB that is required. So just to give a proper picture, this is 72 MB, right? So I'll take only here. And this is 84 MB. But this is from where? I have R4. So 84 MB. So what is left out? 16 MB is left out, and that becomes your block 4. 16 MB is recorded, but this will be empty. Block will be generated, but this will be MB. I'll have only 16 MB left out. This is how your blocks are created. Now, blocks means they're physically stored, guys. So that means if I have a cluster, let's say I'm storing like this, and this is name node, assume. So block 1, block 2, block 3, let's say block 4. This way, randomly we are storing the blocks. When I say randomly storing the blocks, physically the data is getting split, guys. Remember, physically. Right? Now, if I talk about this data set here, records, this records is nothing but collection of rows, right? I might have x1, x2, x3, so on and so forth, x100. Right? This is my data. I want to perform some kind of transactions on this particular data set. I will perform some transactions on this. So would I be able to do it? Would I be able to do it, guys? Because when I'm assigning a task to this node, it is taking block 1. But in block 1, you have row 1 and row 2 also. In row 1, you have the complete row, x1 to x100. But in row 2, you'll have only x1 to x28. What about all this information? How can you process that data? Will that be practically possible? What do you think? Will that be practically possible, guys? You're not passing full data here to do any kind of processing. So this is not possible. So when you talk about blocks, remember they are physical, and because of the physical partitioning of the data, processing on this might not be feasible. It will not be feasible. So Hadoop comes up with a concept called as split. We call it as input split. Now, input split is logical breakup, logical partitioning. So what we do here in logical partitioning is, let's say I decide, based on the data that we are dealing with, I decide that my input split should be 200 MB. We decided. right? Logical partitioning, remember. So input split is working on these physical blocks which are partitioned to create the logical partitioning for ours to run the map jobs. So input split 1. Remember, it needs to have 200 MB. So what I do, I take block 1 first, which has 128 MB, right? So it contains R1 plus R2. But R2, part of R2 is there in 200 MB, in B2. So I'm reading the information, reading the data, record 1 and record 2 from block 1 and block 2. Remember, it is logical partitioning, right? So I'm going to split this data like this, or I'm basically gathering the data like this. R1 plus R2, right? Then I would take input split 2. This is, remember, 200 MB. Okay, so I'm going to take input split 2 now, and I would start reading block 2, which gives me record 3 plus record 4. Record 4 is available, record 3 is available in block 3, and record 4 is available in block 4 as well. So this is 200 MB now. Right? This is basically what we do. Like this. Remember, this is logical partitioning. This is physical partitioning. This is blocks, which is physical. This is input split, which is logical. Now on input split 1, we run map task. Right? So how many splits I have? 2. So I will have 2 map jobs which independently run on these blocks, these input split files. Now I have record 1, record 2, full records, right? All the 100 features and 100 features here. So I will be able to perform some kind of a transaction or valid right, work or valid retrieval job on that data. Making sense? Input split? Any questions here? Very important concept, guys. Is it clear? Input split. Yes, Ashna.
Sir, for example, here we have one file, right? The file is composed of 100 MB, so it's total of 400 MB, right, sir?
Yes.
And then we follow the 128 MB rule. So for the R1, we have the whole 100 MB, and the R2, which we have 28 MB. So from this one, we convert this one to input split, or is this another partitioning?
Okay, see, this is a external source. Okay, this is a single file. It is an external source.
Yes.
Now you want to copy this onto your cluster.
Mm-hmm.
So how is it happening? This way it copies.
Mm-hmm.
Block 1 goes and sits in one particular node. But block 1, what does block 1 contain? 128 MB. So it is physically splitting these records like this and store that data, flatten this data and store it here.
Okay.
Then block 2. So remaining this, and from here record 3, some part goes into block 2. Mm-hmm. So on so forth. Physically, we are splitting this data like this and then storing those blocks here.
And then we convert it to input split for the logical partitioning.
Exactly. So okay. On blocks, Once you get the blocks, on the blocks, we are working to create these input splits.
Okay, understood, sir.
An input split can be of any size based on the data that we are working on, based on the transaction that we are doing. We can decide the input split. Whereas this block size is fixed. We cannot change this. This is fixed, right? And there are multiple calculations, multiple rules that we can apply, right? Look into to apply the input split size. But typically, input split size would be equal to your block size. Typically, that's general practice. But in these kind of cases, it doesn't work, right? So there you will have different size. So this is about input split, which basically allows us to process the data. All the blocks come here from data node in this example. Yeah, blocks are there in data nodes only, right? Physical blocks are nothing but the physical partitions of the data that we are doing. No, different block, right? This is one block, this is two, this is three, this is 4, 5, 6, 7, 8. So I have 8 different data nodes. My blocks are sitting in block 1, block 6, block 4, and block 5. Different blocks, different data nodes, sorry. Yeah. Right. So remember, guys, input split is deciding on your map jobs also, number of map jobs. Okay. Okay. Now we have drawback. So should we continue drawback tomorrow? I'll talk about what is required today so that we can start off with the installation also tomorrow. So we will talk about the drawbacks tomorrow. For now, let me look into, where is this? Here, let me write. So we need to install softwares probably tomorrow. We'll start with creating VMware instance. VMware is a software that you will have to download. If you're using Windows, I would recommend using VMware. If you're using Mac OS, then there is something called as virtual box. You will be using this. Okay, virtual box. These will create a virtual machine for us. Now, in this virtual machine, once we create it, we will install Linux operating system. Because the Hadoop software that we are going to work with has to be installed on Linux operating system, because the commands that we are going to run on HDFS, remember, these are designed to work with distributed file system, which actually works with underlying Linux operating system only. And the commands that we are going to learn are very similar to Linux operating system commands. For that reason, we have to use Linux operating system. If you already have a Linux operating system, fine. If you do not have, then you can create this virtual machine, and we are going to use a free software, free operating system, which is called as CentOS. Okay, all these are the operating systems. I mean, CentOS is a free operating system that we are going to use, and these are the softwares that we are going to install. So VMware, where do I get VMware? Let's go to the link. All you have to do is vmware.com. You better download all these things and keep it ready. vmware.com. It automatically chooses the country you are in. That's okay. And then you click, just hover your mouse on this downloads option. Under the downloads option, you see free product downloads. Here you are going to download this VM workstation player. Okay, so you're going to work with workstation player, this one. Okay, the middle one. You will also have VM. Don't get confused. There is something called as Workstation Pro. This is licensed version, guys. We'll not use that. Remember, we need player. Workstation player. Click on it. It will redirect you to a page where you will be able to download the software. And if you're already on Linux operating system, nothing to do. You don't have to do this step. If you are using Windows, then prefer this. Download now, right? Click on that. If you are on Mac, then go to virtualbox.org. I'm sharing these links here. Click on downloads here. And if you are on Mac, then click on this to get your software downloaded. This is for Mac, VirtualBox. You can also use VirtualBox for Windows also, but I wouldn't recommend this because the screen resolution and all those things will be very small. For Mac users, extremely sorry, I cannot help. Why I'm saying that you will see when you actually install this. Okay, so VMware. Unfortunately, VMware is not developed for Mac. It's only for Windows. Okay, another software that you need to download and keep ready is the operating system, guys. Now, this is around 4.5 GB. Now, this software is CentOS.org. CentOS is one of the operating system flavor that we use. And here we are doing CentOS Linux. Click on this, CentOS Linux, or you can also directly go to download. But let me click here. And here we have CentOS 7. Don't go for 8. Better to go with CentOS 7 because it's more stable. Excuse me. Now, ISO image is what we need. Irrespective of whether you are Mac or Windows, you need to do this download. 8664, x8664. Click on this. I'll give the link. Yeah, you can create in AWS also. Yes. Yeah, so this is the link where you will be able to get the ISO images. You can click any of these links. In my region, these are the links which are close by. So I'm going with the first link. You go to any link, you will have the same files. Now, what you need is DVD ISO, this one here. 4.4 GB. You can see CentOS 78664-DVD-2009 ISO. If I come back and click on HBCSC, you can see here also, you will get that same 4.4 GB file. You go to any link, just read that particular link, the details, and download the value, which is 4.4 GB file. Okay. Don't install other options. It would unnecessarily waste your time. Install or download this. These are the 3 softwares that we need, or 2 softwares to be precise. Right? Once we have this, tomorrow we will start installing and we'll start hands-on. Yes, Ashna.
Sorry, sir. For the installation of the CentOS, do we need some partition? Because at the initial of the installation, there will be partitioning, right? So that we can try to install it by this night.
Not
And
required. You're using Windows?
yes, sir. So currently I'm using a VMware. So I want to know if there's a certain partition inside the CentOS that I need to do. Like
Not required.
not required. So by I will go with the default partition like /home/tmp and everything by default.
Yes, yes, yes. It's
Okay.
just like any other Linux operating system.
Okay.
You,
Thank you,
you are
sir.
already using VMware?
Yeah, I'm using it.
Oh, then you just create a new instance using CentOS. That's it.
Yes. Mhm.
And when you're creating it, it will ask for the storage space. You basically have to give a path and
Yeah,
size.
that one also, sir. How many do we require for the
30
space in the
GB. 30
memory?
GB is maximum you need.
How many? I'm sorry. How many, sir?
30 GB.
30 GB. Okay.
Yeah, that's
And
the
then for the
maximum.
core processor, how many, sir, do we need?
Processors, we can start with 1, but memory is important.
Okay, so one processor, 30 GB of ROM, and how many per RAM, sir?
RAM, if you can allot minimum 4 GB, it would be good.
Okay, sir.
Yeah,
Thank you.
we'll discuss that tomorrow when we do it. If you want to do it ahead, fine. But tomorrow I will be explaining all this. Right, so these are the links, guys. I've shared the links. Make sure that you try and download it. It will take time to download, so I'm giving you these links so that you can upfront download and keep the softwares ready. Okay, VMware for Windows, VirtualBox for Mac users, and then CentOS DVD 2009.ISO version, which is 4.4 GB file. These are the minimum things that you need to have ready tomorrow. All right, so we'll conclude it here. Now, I would request all those people who have joined for professional course, right? Professional program, share me your email IDs. In private, do that. You cannot work on the system, Srihari. Minimum 8 GB is required. If you remember, I told that. Because you need to give 4 GB memory to your virtual machine. Right, wonderful. Yeah.